let's see what is your value. Something around this value. So 20 minus 6.8.69 times 7.81 times 0.9 plus 431. Your value 351. Very close to your number. We're not accurate using a chart. Not accurate 100%. We just estimation. But this value is accurate enough. Okay? Or you can use the second equation, but this one is very easy because everything is given. Phi in plastic, BF, LP, and you can figure out every term in your equation.
Did you say where we got CB from?
Yeah, one more time. CB in this problem is given, that's right. But if you would like to get the actual value of your CB, go back to your beam. What is the type of fluid in your beam? If your type of fluid only one concentrated fluid, okay, go ahead. What is the point of support? Do you have support at the beginning and at the end only? Your CB equal 1.32. If you have two concentrated fluid in your beam, okay, go ahead to this case. How many lateral support points? Do you have two only? Your value will be 1.14. Do you have 4 supporting points? Lateral support means, do you remember this figure? This one? So maybe your beam between this abutment and the next abutment, we don't have intermediate bracing. So we have only support at this location and support at the end location. But we have intermediate bracing, maybe every 10 feet or 15 feet. So we have many points supported your flange. So how many points of support? What is the type of your load? You can figure out what is the value of your CB. If you have different value of CB, for this part, we will use CB 1.67. For this part, 1.11. For this part, 1.11. For this part, 1.67. Use the lowest value to give you the lowest design moment to be more safe. If you have different value of CB for different part of your beam, use the lowest one to get the worst case. Yeah, go ahead.
So on this equation for design moment, why did we multiply by 0.9 for the BF and not for the plastic moment?
This one? Because this term, Phi in plastic, as two terms given in one column in your table. Go back to your table. What is the name of this column? Phi in plastic. So this value 431, not M plastic only. If you would like to get your M plastic only, use your ZX time FE. But this term, Phi in plastic, both of them multiplied together give you 431.
On our chart it has the V times BF.
Say it again.
On our chart, this one, our
Do you have the same chart?
No.
We have many different charts. We have first chart, if you remember, only can give you what is the section properties. This chart called design of beam will be specific, more in terms used in design. The first chart is specific in section properties. This one is more specific in design. So this column, Phi MP, one term, 431. So this term, Phi MP, 431. For example, BF times Phi
is 7 point.
Actually, the term given here is BF only.
Yes.
BF only. So this value need to be multiplied by phi, 0.9. So based on your table, I can figure out I need to multiply by 0.9 or not, phi or not. Okay? So be sure about
Same number, but I was just asking.
the correct table.
This is saying like when we have this AISC chart, and it has phi times BF, but it's the same number as it's still 7.8 as up there. So I was just asking, making sure.
This one?
It's like we have an AISC.
Okay,
chart.
okay. What is the title here? What is the title for your column?
Dang, I just lost it. It's W shapes.
Yeah, I know. What is the title for this column, for 121, this column?
It's plastic moment times phi.
Yeah, you said phi time plastic moment.
Yeah, but then on the BF, it's also multiplied.
Scroll down, you can see it.
Yeah, scroll down. Because it's the same numbers, I was just asking.
Okay,
why.
let's start first. What's your question?
My question was, why is it on this chart, it says phi times BF, and we have 7.81, and then we multiply again times 0.9 for the equation?
What chart are you?
I'm on the AISC.
Which equation?
It's on
This-
page 10.
Just scroll that, please scroll down, because it's gonna make more sense. It's gonna make, I sound crazy, but it makes
Okay,
more sense.
go down.
Yeah, scroll down.
More?
Yes.
Okay, that one. Keep going down one more. Oh,
No,
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 somebody. Okay, at 1468, we have the same numbers, but said, the
Okay.
title of it says it's already multiplied times phi.
1468.
Oh, yeah.
And
And then if you
Yeah.
don't,
They're the same numbers, except that one says it's multiplied by phi already.
431.
No,
Yeah.
yeah.
The other one.
BF.
BF.
right there.
The-
This one?
Yeah.
Yes, it's 7.81, but if you go up and look at the top of the chart, it says multiplied times
Oh,
phi already.
yeah, you are right. But I believe this table.
Okay, I mean, it doesn't matter to me.
Yeah, that makes sense right now. This one subtracted from AISC, actually,
Okay.
the actual handbook. But this one,
Same numbers.
is different.
And
Coming
if you
from FE
use that 0.9,
Handbook.
you still get.
FE handbook, not official textbook, but the first one is official.
Okay.
Okay, so you are right. Based on what is your value of BF, if the value phi BF is given, okay. If BF only is given, so you need to multiply by 0.1.
Okay.
Okay, so I trust the first table, but I don't trust this one, because this one is coming from text handbook for FE. Okay, thank you.
It's the same numbers.
From structure analysis, your beam under given load, you can draw actually 3 internal forces. Mainly, the first one, your shear force diagram. This one called shear force diagram. The second diagram bending moment diagram. We need your maximum moment here, which called M ultimate. This M ultimate must be smaller than or equal, our design philosophy. Phi Mn. Your ultimate moment from your structure analysis must be smaller than your design bending moment from your calculations. That's right. We have another diagram. We have shear force diagram. The maximum value of this diagram called V ultimate. V ultimate is the ultimate shear value from shear force diagram. This value must be equal or less than your design shear capacity or strength. The same philosophy, everything's the same. Your factored internal force, maybe moment, maybe axial force, maybe shear, must be smaller than or equal your design value. But just quick review, if you would like to get your shear stress for any cross section equal VQ over IB, just a quick hint, reminder, V, your shear force, Q, first moment of area, I, moment of inertia, B, your cross section width. If you try to draw shear stress distribution based on mechanics of material for a cross section like wide shape, you can get something like this. We will start at this location, then just before, just after, and at your centroid, put your number, you can get this shape of shear stress distribution. I don't care about this shape. It's not our concern right now in this course, but I need to focus on something. What do you think? Can you watch this flange? This flange supported your shear force only by this part. This flange supported your shear force only by this part. But your web, this part called web, supported your shear force by this area. So, in steel design or in steel structure, shear force is mainly supported by web of your cross section. Next week, in concrete design, I will say, hey, for any concrete cross section, we have two things. We have concrete and we have something called stirrups. Both of them will support your shear force. But in steel design, in steel structure, we have only one cross section. We have only one material, which is steel. But we have different parts in your cross section. Mainly, your web supported most of the shear force. So, this is the reason why we said your nominal design shear equal 0.6 time F yield time area web. Your area web equal D time T web. D, the total depth of your cross section. T web, the thickness of your web. That's all. We will not use the gross area of your cross section. No, we will use the area web only because mainly your web is supporting your shear force. So your nominal design shear equal 0.6 time F yield time area web. Your design shear must be multiplied by phi V to get your design. Your nominal must be multiplied by phi factor to get your design shear. And phi, we have different value for phi. You can assume it 0.1, take it 1. Actually, it's more complicated to determine the actual value of phi. Let's do this example quickly. Just a quick hint. If you have member under tension, from structure analysis, we have a value called B ultimate tension force or tensile force. This value must be smaller than or equal 0.9 F yield area gross. This value must be smaller than or equal 0.75 F ultimate area effective. If you have compression member, from structure analysis, you have compression force coming from laser. For example, this value must be smaller than or equal. Anybody remember what is the value? 0.9 F critical area gross. That's right. If you have bending or a moment in beam or whatever, we have M ultimate. From structure analysis, you draw bending moment diagram. Maximum value of your moment, M ultimate. Must be smaller than or equal phi Mn. To get your phi Mn, actually you have two situations based on what is the length and supported length and relation between LB and LP, and maybe something like this. So this one will be direct calculation, this one needs some more calculation. If you are talking about shear, so we have something called V ultimate from your shear force diagram from structure analysis using RISA or use your hand.